Hello friends, welcome to my channel. Let's have a look at a newly appeared problem, that is problem 2401, longest Nice subarray. In this problem, or in this video, we're going to share a solution based on two-pointer sliding window method. So this method actually is very standard, but in this problem, we're going to use some bitwise operations to help us for the solution. First, I'll read through the statement of the problem, and then we do a simple analysis and finally share the code. Let's first look at the statement. So we are given an array called nums consisting of positive integers. So we call a subarray of nums nice if the bitwise add of every pair of elements that are in different positions in the subarray is equal to 0. So we are required to return the length of the longest Nice subarray. So a subarray is a contiguous part of an array. So here is a note. So subarrays of length 1 are always considered nice. So in other words, if the array in this problem is not empty, so the result is at least 1. So here are two examples. So example 2 is sort of simple. So it's an edge case, we can regard it as. So in example 1, so the longest Nice subarray is 3848. So here is the explanation. So we are going to explain this example in more details later. So let's also look at the constraints. First, the length of nums array is bounded above by 10 to the power 5. So this actually defines the size of the problem. Secondly, the elements of the nums array are in a range between 1 and 10 to the power 9. So with that said, so we are ready to look at the methods or the analysis. So the method is the standard two-pointer sliding window method. So the idea is straightforward. So for each index, so we try to find the leftmost index L such that the closed interval from L ending at I corresponds to a Nice subarray. So for such a Nice subarray, the length is I minus L plus 1. Then overall, we just need to find the longest such interval. Then we can get the result. So here, a subarray is good if the set of indices for 1-bit positions for each number in the subarray is disjoint from that for other number. So we can have a look at example 1. For example, 3848 in this problem provides a good subarray. So if we look at the binary representation of these numbers and the corresponding 1-bit positions, so for 3, the 1-bit position is in position 1. For 8, the 1-bit position is in position 3. And 48, the position is 4, 5. So these three sets are disjoint, right? So with that said, let's look at the procedure. So we're going to use a running variable. We'll call it current union to compute the bitwise OR with the current numbers, say nums I, when we linearly traverse the nums array. So when we find that the current union and nums I has a non-zero add result, so we shall push the left pointer, say L, to the right to remove numbers from the current union to recover the state, the current union add nums I equals 0. So the removal effect can be achieved by using exclusive OR. So the reason is that exclusive OR is commutative, and a number and itself, if we do exclusive OR, we will get 0. So for example, if A exclusive OR with B exclusive OR with C equals the current union, then if we do exclusive OR using the current union with A, so the effect corresponding to remove A in the current union. So before we write the code, here is an important remark on the monotonicity. So the procedure works effectively due to the fact below. So if L1, so this is the I1 is the index associated with L1, the leftmost, the pointer. So I2 associate with L2. In other words, L1, I1, and L2, I2 are the two intervals corresponding to two longest Nice subarrays. Then if I1 is less than I2, and then there must have L1 less than or equal to L2. So this monotonicity actually is important for running the procedure, because if we look at the later indices, we do not need to start over for the left pointer. So with that said, so we are ready to look at the code. The code actually is very short once we realize the above procedure. So first, I'm going to initialize a result variable. So the result will store the longest Nice subarray length so far. So let's also initialize a left pointer, that is L equals 0. So I'm going to use length m equals length of nums equals m, just for convenience. Then the running variables called current union equals 0. And then we can compute the corresponding left pointer for each of the red pointer I. So for the red pointer, I'm going to use a for loop for I in range m. And then we're going to push the left pointer to a state such that the current union with the current number and will be 0. So while current union and nums I is not 0. So in this case, so what we're going to do is that, so we're going to do removal, right? So current union. So we can do exclusive all. This plays the role of removal, right? So nums L, and then we increment L by 1. So after this while loop, so we actually have a state, the current union and nums I must be 0. So in this case, so in order to prepare for next round, we're going to update the current union. So to be the union with the current nums I, right? So for the current state L and the current I, so from L to I corresponds to a longest subarray ending at index I. So because of this, so we're going to update the result state. So it's the maximum of its previous state and the current length, that is I minus L plus 1. So that's it, right? So now we just need to return the result. In other words, after this for loop, so we get all the possible longest Nice subarray ending at index each of the index I. Then the result should be the longest Nice subarray overall. So let's first do a special case check. Yeah, it passes the first example. So now let's look at the generic case. Yeah, it passes the generic case. So I guess for this problem, so that's about it. So let's give a quick summary. So here we used the standard two-pointer sliding window method. So here something that are important are the following. First, so we are using bitwise operations here to help do the solution. Secondly is the monotonicity in the procedure, so which is actually essential for running this program in a linear fashion. So with that said, I guess that's about it for this video. Thank you very much.